Right. See, in rigid system, okay, I have a tertiary butyl group here. So this is actually a rigid system. See, suppose if I have some electron withdrawing group, say the X may be OH group or OAC group or bromine atom, okay, electronegative group, so that it pulls the electron density. Okay, if the X group and the hydrogen atom in the next carbon, adjacent carbon, if it is in axial position, say this is axial, this is also axial, so we say that these two are in periplanar conformation. Okay, so the hydrogen atom, this axial hydrogen and this axial X group, right, they are both are diaxial and they are present in adjacent carbon, so they must be anti-periplanar. They are anti-opposite, so they are anti-periplanar. When axial hydrogen and the X are in anti-periplanar and if the system also rigid, so here flipping is difficult. In this case, this X group, the electronegative group, reduces the coupling constant. Okay. So for example, see here, we have an equatorial hydrogen here and we have another equatorial hydrogen here. Okay. Now listen carefully. In this case, the coupling constant between the axial hydrogen and the equatorial hydrogen. Axial hydrogen is present on carbon 1 here. Suppose this is carbon 1, this should be carbon 2. So it is a vicinal coupling. In this vicinal coupling, system is rigid and we have an electronegative group. Okay. And the electronegative group and the axial hydrogen, they are anti-periplanar. In this case, the coupling constant between this hydrogen, axial hydrogen and the equatorial hydrogen, right? When X is periplanar with HA, this coupling constant is less compared to, listen, see here. Now the X group is in equatorial position and we have hydrogen atom which is in axial, and this equatorial hydrogen, axial equatorial hydrogen coupling constant in this case, it is greater than the axial equatorial coupling constant in this case. Okay, it is due to the electronegativity group present in the axial position, which makes in this case that X group and the axial hydrogen of the adjacent carbon they are anti-periplanar. When they are anti-periplanar, okay, then the coupling constant between the axial hydrogen and equatorial hydrogen reduced. Okay, so keep this in mind, very, very important. Okay, take two. And remember here, this is very important. See, why we are discussing this specifically. Listen, the angle between this axial hydrogen and this equatorial hydrogen, okay, will be close to 60 degree. Similarly, here also the angle between this axial hydrogen and this equatorial hydrogen, this is also close to 60 degree. So if the angles are 60 degree, okay, the dihedral angles are almost equal. Therefore, we expect that the two supposed to have same coupling constant. Axial equatorial coupling constant here and axial equatorial coupling constant here. We expect that these two supposed to be equal, but the presence of this X group in the axial position, okay, and also that this X and the axial hydrogen of the adjacent carbon, they are anti-periplanar. In this situation, this electronegativity group reduces the coupling constant. Okay, right? Take it. This is very important one. And see what will be the expected value? Listen, the expected value. Okay, let me give one example so that it will be clear. Okay, take it. Yes. So the next molecule is coupling constant in alkenes. Observe this carefully. In alkene, we may have geminal coupling. Okay, the bond, see, between the two hydrogen we have two bonds, 1, 2. So it is called geminal coupling. Between these two we have three bonds, here one, here one, here one. We have three bonds. So it is vicinal coupling, but the two hydrogens are in the same side. So it is called cis coupling. Right? This is cis coupling. And here, see, these two hydrogen, here also the bond, number of bond is 3. See, 1, 2, 3. Therefore, this is also vicinal, but the hydrogens are trans. So we say that this is geminal coupling, this is cis coupling, and this is trans coupling. Observe this carefully. If you compare these, listen, in alkenes, compared to geminal coupling, cis coupling is larger. Compared to cis coupling, trans coupling is larger. Okay, so coupling constant for trans hydrogen is generally high. Okay, let's keep this in mind. And what will be the range of these coupling constants? For geminal coupling, right, the value is actually 0 to 5 Hertz. It goes 0 to 5 Hertz. Usually it will be around 2 to 3 Hertz is the usual value for geminal coupling path. Listen, just by seeing the value we can easily identify. For geminal coupling, the value of coupling constant should be close to 2 or 3. Okay. Then the cis coupling constant, right, the value is actually from 7 to 11 Hertz. 7 to 11 Hertz. And for trans coupling, the coupling constant is somewhat high. It goes from 12 to 18 Hertz. See, coupling constant, this is the way I am giving you the range. Okay, if coupling constant is high, then it should be trans. The coupling constant, if coupling constant value is high, then it is due to the coupling of trans hydrogen. Okay, very simple. Right, now listen here, I have given a question. See, this molecule, right, it's an alkene system. In this carbon, a chlorine is attached, and in this carbon, a carboxyl group is attached, and the doubly bonded carbons have one hydrogen. Each carbon has one hydrogen. So, there are two possible isomers here. One is cis isomer, the other one is trans isomer. Let me draw the structure of cis isomer. Listen, in cis isomer, the two hydrogen atoms are in the same side, and the chlorine and carboxylic acid group are in the same side. This is cis isomer. And what about the trans? Let me draw here. In the trans isomer, the two hydrogen atoms should be in the opposite side, and chlorine and carboxylic acid should be in the opposite side. Okay, this is cis isomer, this is a trans isomer. If you take the NMR spectrum, if you record the NMR spectrum, for carboxylic acid we get one signal. Yes, we get one signal for carboxylic acid. Then, listen, for these two hydrogen, they are chemically non-equivalent. So this will give one signal, this will give one signal. The signal of this proton is splitted by this hydrogen, and signal of this proton is splitted by this one. So I'll get two doublets. Okay, one doublet for one proton, another doublet for another proton. Listen, even for trans isomer we get the same kind of spectrum. We'll get a peak for carboxylic acid. This is for carboxylic acid proton, and we get a doublet for one hydrogen and another doublet for another hydrogen. So for both cis and trans isomer will give NMR spectrum in a similar manner. Then how can we distinguish these two? How to distinguish? Very simple. Measure the coupling constant. Okay. See, I have given two coupling constant value. Can anyone tell me which coupling constant corresponds to which isomer? Which coupling constant corresponds to which isomer? So, for trans, the coupling constant, see, just compare the two coupling constant values. Here I have 14 Hertz. Okay, a larger coupling constant, which implies that this should correspond to the trans isomer. So, this corresponds to a trans isomer. Right? And the lower coupling constant value corresponds to cis isomer. So, if you get the spectrum of the two isomers, if it is possible to measure the coupling constant, then from the coupling constant value, we can very easily say which spectrum corresponds to which isomer. Okay, take a look. Very important. Here I have given alpha D glucose and beta D glucose. Right, in the chair conformation, I have given the structures. You know very well, in alpha D glucose, at carbon 1, this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon number 5, and this is carbon number 6. I'm very sorry. This is hydrogen, this is carbon number 6. Okay. Similarly here, this is carbon number 1, 2, 3, 4, 5 and 6. Okay. Now if you compare the two structures, listen, except carbon 1, the remaining remaining carbons in which the groups are similar. Okay. Right? OH groups, all OH groups are in equatorial position and hydrogens are in axial position. Only in carbon 1, okay, in the case of alpha D glucose, OH group is axial. Whereas in beta D glucose, at carbon 1, the OH group is equatorial. Right? Now if you record the spectrum for alpha D glucose and beta D glucose separately, we get two spectrum. Okay, tell me which one corresponds to which isomer. Listen, in both these cases, right, in both these cases, listen, see here I have a hydrogen atom, one hydrogen atom in axial position, and in carbon 1 we have an hydrogen atom in equatorial position. So here the coupling between these two hydrogen, okay, it is actually something like cis coupling. Whereas here the two hydrogens are axial, so this coupling, it is actually trans coupling. This is cis coupling, this is trans coupling, and this molecule is rigid also. Flux, it is, the flipping is difficult here, so it is almost rigid, right? So cis coupling, trans coupling, if you compare, the coupling constant for trans is larger generally. So here we have coupling constant of 4. See, this large peak is due to OH proton. All the OH protons will give a large peak. Okay, so this is OH. It's very simple. And here we get a doublet. We get a doublet, and here also we get a doublet. Listen, it is because of the coupling. Right? Here the coupling is 4 HZ. Here the coupling is 8. So coupling constant is large here. So this corresponds to the trans, or also called beta D glucose. This is beta D and this is alpha D. Okay. This spectrum corresponds to alpha D glucose and this spectrum corresponds to beta D glucose. Right? Can you see any other point here? Okay. Listen. See, in carbon 1, just notice these two. In carbon 2 also, both the isomers are both the alpha D and beta D have same structure. In carbon 1, see, in carbon 1, hydrogen, here hydrogen is axial. In carbon 1 of alpha D glucose, hydrogen is in equatorial. And I have told you, equatorial hydrogen always appear downfield. Okay, downfield, see, it is appearing in downfield. Downfield means a larger chemical shift. Okay, so here the signal appear in the upfield, whereas here the signal appear in the low downfield. Downfield means, right? Downfield means it corresponds to equatorial hydrogen. Equatorial hydrogens appear in the downfield. Okay, take two. Yeah, try to answer this question. Among the two, which one has larger coupling constant? Okay, this is cis-decalin and this is trans-decalin. Okay, this is carbon number 9 and 10. Similarly, this is 9 and 10. Coupling constant for cis-decalin, coupling constant for trans-decalin. Okay, which one is larger? Always trans. Remember, always trans.
Is higher, sir.
Trans hydrogen coupling constant is larger. That's all. I'm not asking the value. I'm just asking you which one has higher value. Okay, generally, listen. See, this is actually rigid system. Trans is rigid system. Okay, so we get a coupling constant which is larger value. Whereas cis-decalin is flexible. Okay, it is highly flexible. Therefore, the two hydrogens, right? They see, this hydrogen is equatorial, this hydrogen is also equatorial, but because of flipping, both become equatorial again in a different manner. So here we get an average coupling constant value, whereas here this is a specific coupling constant value. Whatever maybe it is, coupling constant for trans isomer is greater. Okay, this is well known, right? Keep this in mind. Now, say this question, right? What will be the coupling constant of this alkyne hydrogen? Alkyne hydrogen. Listen, normally the coupling constant value for alkyne hydrogen, right, is actually it should be what we expect normally is that we should get a singlet. Am I right? Listen, I have an hydrogen. For this hydrogen, we expect.
Yes,
so what we expect? We expect that this hydrogen should give singlet.
Singlet.
Because there is no, in adjacent carbon, there is no hydrogen. But here, this hydrogen, see, you have two hydrogens. Let me show one hydrogen like this. Due to hyperconjugation, right, this hydrogen, right, has some coupling with this proton. Okay, and the coupling constant value, right, for, see, this is 4-bond coupling, observe carefully, it's a 4-bond coupling, right. In the case of alkynes, this 4-bond coupling will occur, right, and the value is 0 to 4 hits, somewhat high. Because of that, what will happen, this hydrogen, the signal of this hydrogen gets splitted. So here, this carbon has 2 hydrogen, so it's split into triplet. So what we observe experimentally is that this hydrogen exists as a triplet. It's not singlet, it is triplet. Keep this in mind. Take it. Sir, go through this question. Yes, hydrogen bonding in proton NMR spectrum. Listen carefully. This is first important point. Chemical shift of hydrogen bonded proton is greater than the chemical shift of free proton. What is the meaning? Why hydrogen bonded proton has higher chemical shift? Listen, suppose I take alcohol. Assume that it is free alcohol. In free alcohol, listen, this hydrogen is connected to oxygen, which pulls the electron density. Therefore, this hydrogen usually appear between 1 to 4 ppm. Okay, suppose assume that a OHP signal appears here. Okay, say for example, I will give some value just for understanding purpose. Let's see, this is 3 ppm. 3 ppm. Free OH group. When the same hydrogen, it is hydrogen bonded. Suppose if this hydrogen, dot, I'll draw another alcohol molecule here. Okay, you know very well, oxygen is partially negative. It has partial positive charge. Similarly here, partial positive. Now, see, this hydrogen is partial positive. Now, between this proton and the oxygen, there is an interaction. What interaction occurs? Listen, this is more electronegative. So, through the hydrogen bonding, it pulls the electron density from hydrogen. Already, this oxygen also pulls the electron density. Now, this through hydrogen bonding also, this oxygen pulls some amount of electron density from hydrogen. Therefore, now the hydrogen, the electron density around this hydrogen decreases. When electron density decreases, then the proton will appear in lower field. So what will happen? The proton, the hydrogen bonded proton will appear. Okay, so see, this is the initial position. If it is free alcohol, it should be here. But now, due to hydrogen bonding, the electron density on hydrogen decreases. Therefore, the proton will appear in low field. In low field. Okay, low field. So, which means this is TMS. This is TMS. Therefore, what happens is that chemical shift value increases compared to free protons. Hydrogen bonded protons appear in downfield. Downfield means larger chemical shift. So, chemical shift of hydrogen bonded proton is greater than the chemical shift of free proton. Keep this in mind. Very, very important point. Take. Listen. The chemical shift of hydrogen bonded proton, the chemical shift value, it is directly proportional to strength of hydrogen bonding. Strength of hydrogen bonding. Okay, you know very well. Depending upon which atoms are involving in the hydrogen bonding, okay, the strength of hydrogen bonding varies. Right? So, the chemical shift of hydrogen bonded proton depends on the strength of hydrogen bonding. If strength of hydrogen bonding increases, if hydrogen bonding strength increases, chemical shift value also increases. Okay, keep that in mind. And you know very well, a proton NMR, it is another important technique available to distinguish intermolecular and intramolecular hydrogen bonding. Okay, it is a very important technique, right? But the usual technique is IR, right? Even we can use NMR to distinguish inter and intramolecular hydrogen bonding. Okay, now listen, let me take an example. See, we will take say para-hydroxy benzaldehyde. Okay. So I'll take, this is benzaldehyde, right? And in the para portion we have hydroxy group. This is para-hydroxy benzaldehyde. In para-hydroxy benzaldehyde, see, between one molecule and another molecule, so let me show this hydrogen like this. This is one molecule, and another molecule, let me draw like here. COH, OH. Between this hydrogen and this oxygen, there is an hydrogen bonding interaction. There is an hydrogen bonding interaction. Because of this hydrogen bonding interaction, right, what will happen? This hydrogen appear in downfield. This is intermolecular hydrogen bonding between two molecules. Intermolecular hydrogen bonding, IMHB. Now listen carefully. In the concentrated, if you take concentrated solution of this compound, concentrated solution, the hydrogen bonding is strong. Okay, when hydrogen bonding is strong, yes, chemical shift value will be large. If I dilute the solution, you take para-hydroxy benzaldehyde, concentrated solution, okay, meaning you dissolve this para-hydroxy benzaldehyde in a solvent, right? But you dissolve more amount of para-hydroxy benzaldehyde so that your solution will be concentrated. In concentrated solution, the hydrogen bonding strength is high. Therefore, chemical shift also high. But if I dilute the solution, add more solvent. If I dilute the solution, what will happen? The hydrogen bonding starts to break. Or I can say the hydrogen bonding, it gets weakened. Okay? Weakening effect will occur if I dilute the compound. If you add more and more solvent, dilution will occur. As dilution increases, if you dilute more and more, chemical shift value will decrease because they are inversely proportional. So if you add more solvent, what will happen? The chemical shift value will change. Listen, this is very, very important. On dilution, if chemical shift value changes, then it should be intermolecular hydrogen bonding. Okay? Intermolecular hydrogen bonding depends on dilution. As on dilution, if you dilute more and more, the chemical shift value decreases. Right? Now, what happens in the case of intramolecular hydrogen bonding? Say, suppose I'll take orthohydroxy benzaldehyde. We'll take benzaldehyde and in the ortho portion we have hydrogen. Now between this oxygen and hydrogen there is an hydrogen bonding. Listen carefully, this hydrogen bonding exists within one molecule, So this is intra, right? Intramolecular hydrogen bonding. Okay, listen, in intramolecular hydrogen bonding, since hydrogen bonding exists within one molecule, on dilution, the distance between one molecule and other molecule may increase, no doubt. But this hydrogen bonding, right, does not get affected because of dilution, because it happened in only one molecule. Okay, so in the case of intramolecular hydrogen bonding, chemical shift of intramolecular hydrogen bonded proton, it is independent of dilution. Even if you dilute the solution, nothing going to happen. Okay, so we can very easily distinguish whether the hydrogen bond is intermolecular or intramolecular. Okay, remember, in the case of intermolecular hydrogen bonding, on dilution, chemical shift will decrease. In the case of intramolecular hydrogen bonding, okay, even if you dilute the solution, nothing, no shift, nothing will happen. The chemical shift remains constant. Okay, it implies that the hydrogen bonding is intramolecular. Okay, yes, so it's a very important one. Keep this in mind. Take. Listen, so the next topic is proton NMR spectrum of alcohols, phenols, carboxylic acids and amines. Why I am taking this? What is the speciality? The speciality is that in all these compounds, the hydrogen attached to the heteroatoms. In alcohol, hydrogen is attached to oxygen. In phenol, okay, aromatic alcohol, right? So in phenol, hydrogen is attached to oxygen. And in carboxylic acid, hydrogen is attached to oxygen. In amine, yes, primary amine, secondary amine, tertiary amines are there. So let me just show one hydrogen. It may be, in the case of primary, it may be primary hydrogen amine or secondary amine, whatever it is, right? Hydrogen is attached to an heteroatom. Listen carefully. When hydrogen atom attached to heteroatoms, then this hydrogen get exchanged between the neighboring molecule. Okay, so exchange of proton occurs in these cases. Okay, that is why I have chosen this, very important. Right? So in this molecule, exchange of proton occurs. Exchange of protons between molecules. Okay, and what information we can get from that? It's very important. Listen. This exchange is very fast. Fast exchange of protons on heteroatom occurs. Because of this fast exchange, okay, it affects the multiplicity or splitting. It affects the multiplicity of the signal. Okay. Listen, hydrogen atom attached to heteroatom like oxygen, nitrogen, right? Even sulfur, thiol I didn't give. Even in sulfur also, the exchange will occur. This exchange is very fast. Okay. Due to the fast exchange of protons, which are attached to heteroatom, okay, multiplicity of the signal get changed. Okay. Yes. What is meant by exchange of protons? See here. Listen, suppose if we take an alcohol, between one molecule and another molecule, see I have shown a molecule A and another molecule B, and in molecule A, the hydrogen attached to oxygen is given as star. In molecule B, it is given simply as hydrogen. Now what will happen? These two protons get exchanged. Exchange of proton takes place. So, and this exchange will occur very fast manner. Right, so this hydrogen will go here and this hydrogen will come here. You will get this. And in next fraction of a second, this hydrogen again comes to this place and this. So, this forward and backward process will occur in a very fast manner. This occur in alcohol, this occur in phenols, carboxylic acids, even in amines. Okay, this fast exchange will occur. What this fast exchange, okay, will make the effect, or what effect this fast exchange will make in NMR spectrum. This will discuss that. Listen carefully. Rate of proton exchange, how fast the exchange will occur. The rate of proton exchange is directly proportional to temperature of the system. If the temperature increases, rate of exchange also will increase. Then, rate of exchange of proton, it is inversely proportional to polarity of the solvent. If solvent is highly polar, in highly polar solvent, rate of exchange becomes less or exchange becomes slow. Okay. If polarity of the solvent is less, then rate of exchange is fast. Right? Keep that in mind. Then rate of proton exchange increases when acidic or basic impurities present in the compound. To the alcohol or carboxylic acid or amines, if acid impurity or base impurities are present, then the exchange rate will increase. See, this is a very important point. Keep this in mind. Suppose if you have a pure alcohol, in pure alcohol, there is no impurities, so the exchange of proton occurs little slowly. If you purchase alcohol, commercial alcohols, commercially purchased alcohol usually contain acid impurity or basic impurity. Presence of acid or base, right, increases the rate of proton exchange. Keep that in mind. Very important. So, rate of proton exchange increases when acid or base impurities are present in the compound. Okay. Then, this is very, very, very important part. Is that residence time of proton on an heteroatom. How long an hydrogen atom, a proton is present on oxygen. Okay, in the case of alcohol, how long this hydrogen is present on this oxygen. If it is present on oxygen for a long period, then the adjacent carbon, hydrogen present on adjacent carbon can couple with this hydrogen so that splitting will occur. Okay, see the hydrogen atom, how long this hydrogen atom present with this oxygen. We call that time as residence time. Okay, residence time of proton on heteroatom, it is inversely proportional to rate of exchange. If exchange rate is high, then it is very difficult to couple this hydrogen with this hydrogen because the exchange rate is fast, so this hydrogen will immediately go to the other molecule. It will immediately go to the other molecule. Therefore, the time, the NMR time scale, within the NMR time scale, the coupling should occur. But this rate of exchange is very fast compared to the NMR coupling time scale. Right? Isn't coupling time scale, NMR, coupling NMR time scale, right, is very small compared to the rate of exchange. If it is very small, then coupling is not possible. I'm sorry. Rate of exchange is fast, right? Therefore, coupling in NMR time scale, if this is less, which means coupling does not occur. Okay, we need some sufficient time for hydrogen to present on oxygen. Then only coupling will occur. If the hydrogen attached to oxygen, if it exists if it involves in fast proton exchange, then it is very difficult for the adjacent proton to couple with that. Okay, so residence time is how long that hydrogen present with this oxygen. That time is called residence time. If residence time is more, then it is easy for adjacent proton to couple, so that you will get splitted signals. Okay, see, as residence time increases, spin splitting with the proton on heteroatom is highly probable. Spin splitting is highly probable if residence time increases. Okay, take note. Suppose if I take methanol, so this is the formula CH3OH. We have two kinds of proton, the proton with the methyl group and proton with the present in OH group. We will get two different protons, so we will get two signals. Okay, if I purchase methanol commercially, okay, listen, the commercial methanol or impure methanol, I can say. Impure methanol, meaning it contains acidic or basic impurities. If impurity is present, then this hydrogen involved in fast exchange. Observe carefully. If impure methanol means the methanol may contain either acid impurity or base impurity. If impurity is present, then this hydrogen exists in fast exchange, or it involved in fast exchange. Therefore, residence time of the proton on oxygen become very, very, very less. So, the adjacent protons, cannot couple with this hydrogen. Therefore, what will happen? This methyl group will give you one signal, and the OH group will give you one signal, right? And the methyl group will give you one signal like this. This is signal for methyl. You know your OH proton will appear in downfield. Okay? Right? We get a signal and both appear as a singlet. This is a singlet. This is also singlet. This methyl proton cannot be coupled with hydrogen, and hydrogen cannot, or I can say the other way, the proton signal of OH does not get splitted by methyl, and the signal due to methyl group does not get splitted by OH. Both appear as a singlet. Okay. Suppose if we take, say, very pure methanol. Suppose if we get pure methanol, 100% pure methanol, 100% pure. In pure methanol, the rate of exchange is slow. See, in pure methanol, this is a point you should keep in mind. Rate of proton exchange. Rate of proton exchange is very low. Exchange is low. Meaning, the residence time will increase. Now, the proton resides on this oxygen for a long period. During that period, the adjacent methyl proton couple with this hydrogen. So, what will happen? The methyl signal, it is splitted by this hydrogen into a doublet. And the signal of the proton attached to oxygen, OH proton, that signal is splitted by methyl group into a quartet. So, in pure methanol, see, the signal appears like this. What will happen? OH proton signal, it gets splitted into a quartet. This is OH signal. And methyl signal, it is splitted by OH proton into a doublet. Okay, I'm just drawing some schematic picture. Don't worry about the intensity and the other information, right? Okay, I'm just giving you the schematic. This is for impure methanol and this is for pure methanol. Okay, so in pure methanol, rate of exchange is slow, therefore coupling will occur. You will get splitted signals. Okay, take. See, in the case of ethanol, the molecular formula is CH3, CH2OH. Now, we have three different protons here. So, we get three signals. Okay. If you take impure ethanol means ethanol containing either acid impurity or base impurity. Okay. In impure ethanol, the rate of exchange is fast. Therefore, the signal for OH proton cannot be coupled by the CH2 proton. There is no coupling. So, if you plot intensity versus magnetic field strength, Bz, what will happen? OH proton appear as a singlet in the downfield. Then CH2 proton, it does not couple with this hydrogen, but it can couple with the methyl. So, CH2 signal, it is splitted by methyl group, methyl proton into a quartet. So, this is OH signal, and CH2 signal, methylene signal, it is splitted into a quartet. Splitted into a quartet like this. Okay, this is signal due to methylene. Right, methylene group. And what about methyl? Methyl proton is splitted by CH2 into a triplet. So, we get a triplet also. This is due to methyl group. So, if you take impure ethanol, in impure ethanol, this is how we get NMR spectrum. Okay, suppose if you take very pure, 100% pure ethanol, right? 100% pure ethanol. Okay, in 100% pure ethanol, the rate of exchange of OH proton is low. Is low, very, very low. So, slow exchange takes place. So, residence time of OH, hydrogen atom on oxygen increases. Residence time is more. Therefore, coupling is possible. In this case, what will happen? The OH signal, okay, the signal for OH proton is splitted by CH2 into triplet. So the OH signal appear as a triplet. OH signal. Okay, now the CH2 signal, it is splitted by methyl and OH. Okay, but the chemical shift of this and this are different. So we should use a different formula. What is that? 3 plus 1, 4. 1 plus 1, 2. 4 into 2, 8. So the CH2 signal, right, it appears as a multiplet. Let me draw like this. It appears as a multiplet. I have told you more than 7 means multiplet. Okay, it appears as a multiplet. Then, actually multiplet means it contains 8 peaks. Keep that in mind. It contains 8 peaks. Then the methyl signal, that appears as a triplet, as usual. It appears as a triplet. This is how the spectrum will appear, appear for ethanol. Pure, 100% pure ethanol. Are you able to understand this concept? Tell me what is glacial acid. This is for
100%.
Glacial means 100% pure acetic acid, correct? Right. In the case of pure acetic acid, how the spectrum will look like? Okay. Anyone tell me? What will happen? How the spectrum will appear?
OH proton on the quarter.
Is your answer correct? Just check it.
No, sir.
How
Not
many?
adjacent.
No coupling. No coupling. Why? Between these
Highly
Protons are not adjacent.
no, they are not adjacent. Very good. Very good. See, methyl protons and the OH protons. See how many bonds are there? 1,
Yes, sir.
2, 3. There are 4 bonds. I have told you, above 4 bonds, above 3 bond, the coupling becomes very, very weak. So, even if you take glacial acetic acid, there is no coupling occur between these two. Therefore, even in glacial acetic acid, it appears as a singlet and this also appears as a singlet. Clear? Any doubt? Right. See, if you take impure amine, this is called ethanamine, right? Ethylamine or ethanamine. If you take impure ethanamine, in impure ethanamine, this hydrogen involved in fast exchange. Therefore, there is no coupling between these two. There is no coupling. So, how the spectrum will look like? Listen. This NH2 proton appear as a singlet. Downfield. Then the CH2 proton is coupled by methyl group into quartets. So, it will appear as a quartet. 1, 2, 3, 4. It will appear as a quartet. Then the methyl proton is splitted by CH2 into triplet. 1, 2, 2. So the signal appear like this for methyl proton and this signal is for CH2 proton. This is impure ethanamine or ethylamine. Okay. If I take pure ethylamine, 100% pure ethylamine. Ethanamine is the IUPAC name. Now I am writing common name, ethylamine. Okay. How the spectrum will look like? This is very, very important. Observe carefully. This is very, very important. Listen, usually due to fast exchange, right? NH2 proton or NH proton, amine protons, okay, it appears as a broad peak. It does not appear like this. It appears as a broad peak. Why broad peak? The reason is, listen, these hydrogens are involved in fast exchange. Hydrogen is involving in fast exchange so that the uncertainty, right? Uncertainty with this proton to interact with the magnetic field is somewhat difficult, right? Or we can say since it is involving in fast exchange, right? There exists some uncertainty. Because of the uncertainty, the NH2 signal will appear as a broad peak. It will appear as a broad peak. Observe carefully. NH2 peak is usually observed as a broad peak. Okay. Now listen carefully. And we have another reason also. Listen. Due to fast exchange, it appears as a broad peak. And one more reason is there. What is that? Nitrogen is a quadrupolar nucleus. For nitrogen, I value is 1. It is a quadrupolar nucleus. Due to quadrupole effect, the signal usually appears as a broad peak. This is another reason for NH2 signal appears as a broad. NH2, NH, these signals usually appear as a broad peak. Okay, if you take pure ethylamine, in pure ethylamine, the exchange rate decreases. When the rate of exchange decreases, then there exists a coupling between these two. So what will happen? NH2 protons get splitted by CH2 into triplet. So this NH2 proton gets splitted into a triplet. Some broad triplet will be there. Okay, then the CH2 protons is splitted by methyl as well as NH2. So 3 plus 1, 4, 2 plus 1, 3, 4 into 3, 12. Yes, we get a signal with a multiplet, which consists of 12 peaks. 12 peaks. It is due to CH2 protons. This is due to NH2. Then methyl proton, it is splitted by CH2 into triplet. It exists as a triplet, okay, as like the impure amine. Okay, so this is how amines, right? Primary amines, NH2, primary amines, secondary amines, right? Amide, okay, right, will exist as a broad peak. Okay, keep this in mind, very, very important point. In all these compounds, fast exchange is there in impure compound, and in pure compound the exchange rate is right. Is the deuterium exchange in proton NMR. Very, very useful study. Okay, normally what we do is that we'll take the compound, right, in the NMR cuvettes. Okay, we'll take the compound and we'll dissolve that compound in a solvent. Okay, we usually take solvent depending upon the compound that we take. Suppose assuming a compound is already a liquid, I'll take a compound which is already liquid, then we'll take the NMR spectrum. So this is NMR spectrum of the compound without adding D2O. Now you take the same solution and add a small amount of D2O, few drops. Add few drops of D2O. What will happen if you put D2O? Okay, if there is any OH group, alcohol group, or phenolic group, or carboxylic acid group, or amine, primary amine group, secondary amine group, if these groups are present, then what will happen? Okay, the number of signals get affected. Okay, so this D2O addition, deuterium oxide addition, is a very important technique in NMR. It is used to detect, so carefully, D2O addition is used to detect the presence of heteroatom protons, OH, whether OH group is there or not, or a phenolic group, or carboxylic acid group, or amine group, primary amine, secondary amine, thiol group, whether these groups present in a compound or not. To check it, okay, just take the compound, first take NMR without D2O, then take NMR with D2O. Okay, so record the proton NMR spectrum of the compound without D2O and with D2O. Right? If number of signals remain same, then these groups are absent. If the number of signal decreased, suppose without D2O I have 5 signal, with D2O I have only 3 signal. Number of signal reduced. If number of signal reduced, then it indicates that these group, any one of these group may present. Okay. Now listen, what is actually happening? Listen, if I have an alcohol group, if I put D2O, what will happen? The deuterium atom exchanges this hydrogen so that this becomes ROD and you get HOD. Now what happens? This OH signal of alcohol, it is now becoming ROD. Okay, therefore there is no OH now. In the alcohol there is no OH. Therefore what will happen? The OH signal, okay, does not appear in the spectrum. OH signal does not appear in the spectrum. That's all. So I have given an example with alcohol. Same thing happened with amines, carboxylic acids also. Okay. Now let me give an example. Before that, just copy this. Yes, correct. Yes. See, in the case of methanol, without D2O we get 2 signal. With the D2O, the OH signal disappeared and we get only 1 signal. Okay. Right. Similar thing happened for ethanol and other compounds. Right. See, here I have given secondary amine. Here also the same thing will happen. Okay. Take.